Instead of a song today, let's take a look at the opening credits from my YouTube series on catapults called Throwing Stones. Today's topic is projectile motion. Now, I showed the opening credits to my video series on catapults for two reasons. One is an obvious, blatant commercial advertisement for my YouTube series, but also I wanted you to take a look at the motion of the projectiles, that is, the things that are launched from various catapults. Let's take a look at some of the catapults that I build during the series. So the flying objects you saw in the videos there were examples of projectiles. Now, you might be saying, well, then what makes them projectiles? Projectiles are objects in free fall that have an initial horizontal velocity. Free fall means, as you recall, that the only force acting on them is gravity, so we're not going to count forces such as air resistance here. And the fact that they are in free fall, i.e. affected only by gravity, but they also have an initial horizontal velocity, means they have a two-dimensional motion. Well, we need to learn how to describe that two-dimensional motion that they have. You can consider some other examples of projectiles, by the way, such as bullets after they leave the barrel of the gun, and baseballs that are thrown unless they are thrown straight up. Now, baseballs do have other forces acting on them that are quite significant, such as air resistance. But in the simplest way to look at them, they are projectiles. So what gives the projectile its characteristic shape? Well, the question we asked earlier is what model of motion applies to a projectile? Is it constant acceleration? Is it constant velocity? In fact, we may have to split up the motion of a projectile into its separate components before we can really answer that question. Let's take a look at a video from another one of my catapult videos where I talk about how the horizontal and vertical motions affect each other, or perhaps they don't affect each other. To answer that, let's compare a projectile to something that is only falling. In this video, I launch a foam ball horizontally a few times. I analyzed the video using Logger Pro and found out that the ball hit the ground in 0.27 seconds. I then dropped the same ball from the same starting height and analyzed its motion. Even though the ball was not moving forward, it still took 0.27 seconds for the ball to hit the table. The horizontal motion did not affect the vertical motion. Galileo studied this by rolling balls off a table. He realized that the independence of horizontal and falling motion meant that projectiles would follow a special kind of trajectory called a parabola. So it seems that at the same time as the projectile is in horizontal motion, It's also in vertical motion and free fall, but the two motions do not affect one another. At the same time as the object is moving forward, it is in free fall vertically. The key phrase being there at the same time. Let's do an analysis then of a projectile from one of my other catapult videos where we can see the horizontal motion and the vertical motion separately. So in an earlier episode of my catapult series, I showed a model of a ballista being fired at a dragon. The dragon was just my little dragon puppet called Smoget. And so let me show you what that video looks like. We're going to insert a movie using our Logger Pro program here. I call this shooting the dragon shots that I recorded for this video episode. All right, there we go. So you can see my little dragon there. Let me show you what the video did. I recorded 3 separate firings of this little ballista device at my dragon. There we go. We'll just analyze one of them. So we'll take my video back to the beginning here. Maybe we'll analyze the first one. What we can do is we can page frame by frame here until we can move a little bit faster forward if you want. Oh, so I want to get maybe in the middle of this one. That was a good one. And I want to get right before it starts to fire is where I want to start my analysis right there. So I'm going to go over here and click on these tools here. And the first thing I want to do with my tools is set the coordinate system. So if you go up here to the top, there's a thing that says set origin. And I'm going to click on that. And I may as well have the origin be the 0 of the position here. In other words, the starting position. I'm going to set that as my origin. I'm also going to set an approximate length. Usually in these things we would put a meter stick or something in the video itself so we could get a length established. I just happen to remember that the distance from the projectile to the nose of Smoget here was approximately, it's very approximate, but I believe it's 1.1 meters. All right, so now we are ready to start marking some points. We go up here and we select in this thing that has some crosshairs over a little point. And then we can come down here and move the crosshairs over to the projectile. And notice it moves a point. Now this video is a little bit, it's not a high-speed video, so we're going to have to approximate where I think I see the front of the little projectile. But I'm going to try to get the front of the projectile each time. And, you know, some of the errors that will accumulate in here will kind of cancel each other out, we hope. So we just keep going, trying to get the front of the projectile each time. Once you go over here, you can see it's actually moving horizontally mostly. There we go. And it's interesting to note that the projectile kept the same orientation in space as it went through its motion here. And there we go. And maybe one more here for good measure. All right. So now we are ready to see the results of our analysis. Let's see what happens when we look at the vertical and horizontal motions of this projectile. And here are the graphs. The red dots represent the horizontal motion of the projectile versus time here, and the blue dots represent the vertical positions of the projectile over time. You can see very clearly that they have their own unique shape. It looks like the horizontal motion is more or less constant velocity, isn't it? It keeps the same distance over time relationship here. Let's see if we can analyze what the velocity was. We can do a linear fit on the x values here. and we find that the slope was about 3.2 meters per second. So that just meant that our projectile in the horizontal motion goes at a constant speed of about 3.2 meters per second. What about the vertical motion? Well, this looks like a parabola to me, but to be sure, what we can do is we can look at the vertical velocity graph. Now think for a moment what you think the vertical velocity graph should look like if this is indeed a parabola. In other words, it has the same shape as something moving in free fall in one dimension. Now the program is very clever. If I say insert graph, it knows that I want a vertical velocity versus time graph here. And that is more or less what we expected. We expected to see that if our vertical motion is just like an object in free fall, that is to say, undergoing constant acceleration in the vertical motion, then we would expect a graph something like this. And I'm only going to select the parts of the graph. I'm going to leave off the first point and the last point because of the way it calculates velocity. Those points might be a little bit suspect, but I'm going to analyze the others, and I'm going to say linear fit, and look at that. The slope of my graph was a negative 9.99 meters per second. Very close to the acceleration of gravity. So that is what we kind of expected, I think. So there's our two graphs, and we're going to use these all the time, this information, to analyze the motion of a projectile. In the horizontal direction, the motion is constant velocity. And in the vertical direction, the motion is constant acceleration with an acceleration of about 9.8 meters per second. So the answer to the question that I posed earlier about what model of motion we should use for projectiles is that we should use both constant velocity and constant acceleration, as we saw in the LogRPro analysis. For the x motion, we saw that the position versus time graph was a straight line. Therefore, the motion is constant velocity there. And for the y motion, we saw that the position versus time graph was parabolic. And we confirmed that by analyzing the velocity versus time graph and seeing that it is a straight line with a negative slope. And the acceleration here on the Earth is about a negative 9.8 meters per second squared. So our equations of motion will be these. In the horizontal direction, we're just going to use our constant velocity equation. Our velocity is going to be the same as it was initially. And there's no acceleration. But in the vertical direction, we have to use our constant acceleration equations. We have the one that gives us the position and the one that gives us velocity if we know the time and the initial velocity and the acceleration. And we have this one. And again, the acceleration is a negative 9.8. Here it says 9.81 meters per second squared. That 9.81 is what you see often in problems and in textbooks. That's a worldwide average. Here in the Houston area, it's about 9.79 meters per second. So let's answer some questions here about projectile motion. A bicyclist is riding at a constant speed along a horizontal straight line path. The rider throws a ball straight up to a height of a few meters above her head. Ignoring air resistance, where will the ball land? And there's your choices. Go ahead and pause the video and then start it up again once you think you know the answer. It's going to end up in the same hand that threw the ball, because the rider is going at the same speed as the ball is moving horizontally. The horizontal motion doesn't change. And so the hand should be right in the position where it was to catch it, just like it was when it was thrown, because the horizontal motion stayed constant.